Okay, so let's continue our discussion about ungaged supergravities versus gauged supergravities, the main motivation why we should be interested in studying the gauging procedure. Remember the scheme I sketched out, I partially sketched out yesterday. If we start from equal 11 superstring theory, or better, supergravity, because we are interested in the low energy description of these theories. Okay, so we can start from the supergravity description in 10 dimensions of these superstring theories. For instance, type 2A or type 2B supergravity, okay? Or equal 11 supergravity, which describes the low energy limit of the so-called M theory, okay? And we compactify, as we discussed yesterday, on an internal compact manifold, which is Ricci flat, in the absence of fluxes. What we end up with in d dimensions is an ungaged supergravity, okay? In a supergravity in which there are no minimal couplings of vector fields to any other. We also pointed out the pros and the cons related to these ungaged theories, in particular that they exhibit an interesting global symmetry structure defined by a global symmetry group G. Okay? If you compactify these theories on tori, in particular that equal 11 supergravity on a torus, okay, of various dimension, what you end up with is a maximal ungaged supergravity in which this group G, in a particular version of the theory, in which all form fields are dualized into lower rank fields. Okay, well, this group G is an exceptional group, an exceptional Lie group. Okay, so this group G is particularly interesting. Okay, and can be very large, quite large. Now, on the other hand, we've seen yesterday, we pointed out that these theories are physically uninteresting. So they are mathematically appealing, but physically uninteresting for the reasons we mentioned. However, if we compactify the same theories on an internal manifold, which is non-Ricci flat, so it's curved, okay, with fluxes. By fluxes, I mean vacuum expectation values of field strengths across cycles of the internal manifold. Well, we end up with a theory which is in d dimensions, which is a d-dimensional gauged super. Why? Well, because the fluxes and the structure of the internal manifold induce in the low energy description minimal couplings of the vector fields to other fields. Now, minimal couplings, for consistency of the theory, have to be associated with an internal symmetry, a gauge symmetry. Okay? Otherwise, longitudinal modes would not decouple of the vector fields, right? So there is an internal gauge group. The structure of this gauge group, okay, depends on the geometric structure of this internal manifold. You have a sphere, if you have a twisted torus, if you have a group manifold, and on the fluxes across cycles of the internal manifold. Okay? So G depends on all these things which describe your compactification. In what sense does this theory describe the low energy limit of this compactification? Well, here we have to be careful because the issue is subtle. What happens is that a suitable subset of the low-lying modes of superstring theory or equal 11 supergravity on this background, okay, are captured by a theory like this. A suitable subset which defines a consistent truncation. Consistent truncation means that all solutions to this model are solutions also of the higher dimensional one. Can be uplifted. Okay, this is the idea. Okay, so these theories are physically interesting from a phenomenological point of view, they are interesting because these fluxes and the structure of the internal manifold induce masses and therefore spontaneous supersymmetry breaking in general. Okay, this is something that from a phenomenological point of view we want to have. It will also induce a scalar potential. Scalar potential uplifts the degeneracy that we have here among the scalar fields, okay, and selects vacua with certain properties. In particular, you can have cosmological constant. So you can have ADS vacua, which are of particular interest in ADS CFT. ADS vacua preserving, for instance, a certain amount of supersymmetry, or no supersymmetry at all. There are. So there is a number of interesting features that all these theories share. Okay. Another interesting feature is that although these lower dimensional theory describe only a subset of the low-lying modes of superstring theory, American theory on these backgrounds, they capture the full nonlinear interaction between these modes. This nonlinear interaction will be very highly, will be very difficult to derive directly from superstring theory or from 11 dimension. It would be very, very difficult. Okay.
So one question. So in the ungauged case, we don't need consistent truncation like in the gauged.
We do need here also consistent truncation. In both cases, we need consistent truncation. So in both cases, we're talking about supergravity, lower dimensional theories which describe consistent truncations. Remember the compactification on a topos. Okay, there the consistent truncation amounted to restricting to the zero Fourier modes in the expansion of the fields. No, in the Fourier expansion of the fields in the coordinates of the internal topos. Okay, and that is a consistent truncation. Okay, for more general Ricci flat manifolds, you can define consistent truncations in a similar way. Okay, here the issue of consistent truncation is more subtle.
So when you just dimensionally reduce and when you compactify, what's the basic difference?
What's the difference? Well, in both cases you are dimensionally reducing somehow, right? But so you are defining a lower dimensional theory describing a subsector of your higher dimensional one, a subsector of modes of fluctuations of the higher dimensional one. Okay, and so in both cases you're defining a consistent truncation, which is an effective, which is described by an effective lower dimensional theory in both cases. However, in these cases, the internal structure of the geometric structure of the internal manifold makes the consistent truncation, defining the consistent truncation more difficult because there are non-trivial interactions between the various modes. So it could be that you truncate, some modes out, okay, but the remaining modes that you retain act as sources due to these interactions, for those modes that you have selected out, that you have set to zero. And in this case, the truncation is not consistent. So defining consistent truncations is a very subtle thing. One way is to use, for instance, the Church-Schwarz reductions. That is to write down the 10 or 11 dimensional fields in a way that their dependence on the internal coordinates gets factorized in a suitable way. If you can do that, then what you end up with is a consistent truncation. Okay, so Church-Schwarz, they give you consistent truncations. Now, within maximal supergravities, there is a general framework for which is very useful for defining consistent truncations. That is exceptional field theory. There you can define some generalized Church-Schwarz ansatz, okay, and that allows you to embed certain lower dimensional gauge supergravity within M theory or maximal type superscale theories. Okay. Okay, so these are the good features of these models, okay, which make them interesting from a physical point of view. Unfortunately, however, in these theories, G is broken. It's broken by the minimal couplings involved in the gauging. Okay, so the global symmetry, which was manifest in these theories, is broken. It's broken by the presence of these fluxes and the structure, the internal structure of the manifold. The manifold, the structure of the internal manifold. Okay.
The problem is the global symmetry. You're referencing the same one that reflected the various dualities.
Precisely, and that's the problem. You see, because this G contained a good part of the known string or M theory dualities. Now, if this is broken, somehow you're losing your track. I mean, you're losing track of these dualities in the presence of fluxes. Okay, and this is something you don't want really. Okay, because then you're kind of losing an important information that different backgrounds are in fact different descriptions of say physics, so that they are equivalent. You're losing this equivalence. Okay, as I will show, there is a formulation of gauge supergravity in which at least formally G is restored. Okay, and this is the embedding tensor formulation of gauge supergravity. So this is the main advantage of working with the embedding tensor formulation. So we have these two different classes of theories, okay, in d dimensions. We shall focus on d equal 4, but I will also touch upon the main features of higher dimensional supergravities. Now we can go directly in d dimensions from one theory to the other, okay, through the gauging procedure. That is, we can obtain the gauge supergravity that originate from these non-trivial dimensional reductions or compactifications, if you want. Okay, we can retrieve, we can construct this supergravity from corresponding ungauged models with the same amount of supersymmetry and the same the same field content. Okay, amount of supersymmetry, same field content, and we can go from one to the other through the gauging procedure. Yes.
Do these gauge theories contain anomalies? And if they do, is there a way of linking the ungauged to the gauged?
This is a good question. We shall focus on extended supergravities. Now, in extended supergravities, you don't have anomalies.
Sorry,
sorry,
what's the question? What's the question? What's the question?
The question was about anomalies. Do these gauge supergravities have anomalies? Now I will focus on extended supergravities. Consider extended supergravities in 4 dimensions. Now, they are non-chiral, so you don't have anomalies there. Okay, but you can play the same game in n equal 1. So you can there in n equal 1 you have more freedom, but you can play the same game. Okay, you can introduce a duality structure and perform the gauging. There you have an anomaly. Okay, there you have an anomaly. So the anomaly will be also related to a particular component of the embedding tensor, as I will show. Okay, but we shall focus on extended supergravity. So we won't be dealing with this issue. Okay. Good. So starting from an ungauged model in d dimensions with the same amount of supersymmetry and the same field content, okay, we can construct a gauged supergravity model of this kind through the gauging procedure. And in fact, when considering extended supergravities, the only way of introducing masses or a scalar potential is through the gauging procedure. Without manifesting breaking supersymmetry at the level of the Lagrangian, is through the gauging procedure. That is, what do we mean by gauging procedure? We mean that a suitable subgroup of the global symmetry group of the corresponding ungauged theory is promoted from global to local. Okay? And the procedure also guarantees that supersymmetry, the amount of supersymmetry, of shell supersymmetry, is restored at the end. Okay? And this requires the introduction of mass terms, Yukawa terms, okay, for the fermion fields, and a non-trivial scalar potential. This scalar potential is directly related to the choice of the gauge group. Okay? So you can go from here to here directly as a shortcut in the dimensions. And all gauge supergravities can be obtained in this way, without having to derive them from a dimensional reduction and a truncation in some way. Okay? Unfortunately, there are several gauge supergravities which don't have, which you obtain this way through the gauging procedure, but they cannot be uplifted to 10 or 11 dimensions. Okay? Or at least whose uplift is as yet unknown. Okay? So this is an open problem. Now, it is useful to encode, and it turns out that one can encode the choice of the gauge group inside the G, the global symmetry group, in an object, a constant object, which defines this embedding. This is a constant object which encodes all these features, fluxes, and the geometric properties of the internal manifold, okay, and which is formally G covariant. If you can formulate this procedure, the gauging procedure, in terms of this object. All these quantities, masses, scalar potential, are all defined in terms of this object, which is the embedding tensor. As we said before, the advantage of this formulation is that now all these modifications that you do on which are implied by the gauging procedure are all encoded in terms of this quantity, okay, which is formally G covariant. And so this means that you can describe the equations of motion. The equations of motion, which here I schematically denote by E, generically denote by E, as functions of the fields of the theory and of this embedding tensor, in a way that is formally G covariant. Because these are G covariant, the fields are G covariant because these are the same fields that we had in the ungauged theory, which was G covariant. Then we have this gauging. But all the changes implied by the gaugings are all encoded in theta and can all be written in a G covariant, formally G covariant way in terms of this theta. Okay? So that for any G in G, this is equivalent to G, I'm writing this in a very schematic way. The equations of motion are formally invariant under the global symmetry group G, provided that together with the fields, we transform the embedding tensor as well. And we know how to do it because the embedding tensor belongs to a particular representation of G. So we know how to do that. Because the embedding tensor is a tensor, formally. So we are transforming both. We are transforming both the fields and the embedding tensor. Remember, the embedding tensor contains coupling constants, contains masses. So it's a non-dynamical object. Okay? So what you're doing here, you're transforming together with the dynamical fields, also a non-dynamical object. So this correspondence, okay, is it's not a global symmetry of a single theory, because different magnetic tensors define different theories. But rather, it is an equivalence between different theories. One described by theta, and the other described by g times theta. Okay? So it's a proper duality, an equivalence between different theories. So you see, using this approach, we can recover, we can systematically study the effects of the non-stream dualities and theory dualities on these non-trivial backgrounds by simply studying their effect on the embedding tensor. As an example, we can consider type 2B compactification of type 2B on a torus in the presence of an H flux. H flux is the flux of the field strength of the Kalb-Ramond field, which is called H. It's a three-form. Okay? One can consider a toroidal compactification in which you give a VEV to the field strength of the Kalb-Ramond field. We're giving a VEV, a vacuum expectation value, to the field strength, which is a three-form of this two-form, okay? Across a cycle of the internal torus. This is a flux. What you end up with in lower dimensions is a gauge supergravity with a specific gauging defined by this flux. This flux defines a component of theta. Now, if you apply some of these transformations, that is dualities, okay, in particular, those which are called T-dualities, okay, which lie in here, then this you see that this H flux becomes a geometric flux. And a geometric flux can become a Q flux, and so on. So, which is non-geometric, okay? So you will see, you can study in a systematic way, using this formulation, the effect of dualities, some of them are inside G, on flux compactifications, okay? And this is a great advantage. All the non-geometric fluxes, they just arise from this kind of action on theta, okay? On theta defining a geometrical compactification. Okay. Other questions?
So why theta is not dynamical?
Oh, because simply theta encodes VEVs, that is background quantities, constant background quantities characterizing our 10-dimensional solution. So it encodes vacuum expectation values of field strengths across cycles of the internal manifold. This is not dynamic, these are VEVs. Okay? You can think of theta, for instance, as being a magnetic flux. No? If you take a magnetic flux, if you switch on a magnetic flux in your laboratory, okay, this is a non-dynamical thing because it is something that that belongs to the environment. Okay, it breaks your rotation symmetry, SO3 symmetry, in space. Okay, however, if you rotate also the magnetic flux formally, your equation of motion of a particle inside it remain invariant, provided you rotate also the magnetic flux. So this is a schematic way, a very simplistic way of seeing this. Okay, magnetic flux is something non-dynamical that belongs to the environment. You fix it. Okay, and formally, you write the equations in the presence of this magnetic flux, but formally, everything is still SO3 invariant, provided you rotate your magnetic flux as well. Okay? Okay. Are there other questions? So, let us start describing the action of the global symmetry group G on an engaged supergravity. Let's see how it acts. let me start from a generic d-dimensional theory. Then I will focus on 4 dimensions. Okay. So d-dimensions, we have a a bosonic sector and a fermionic sector. They are related by supersymmetry. Okay. So we are considering a theory with a certain amount of supersymmetry. We are focusing on extended supergravities, meaning that the generic supersymmetry parameters depends on a number of independent functions which is greater or equal than 8. So extended supergravities. In 4 dimensions, this means n greater or equal than 2, because each supersymmetry generator contains 4 supercharges. So this means n greater or equal than 2. But this is a dimension-independent way of counting supersymmetries. So we have a bosonic sector. Which contains the metric. Then it contains the scalar fields, S running from 1 to n s. Okay? In general, this is. They contain these fields. And besides scalar fields, it will contain in general p-forms, p-form fields, namely rank p antisymmetric tensor fields. Okay, with various p's. For the p equal 1, we have the vector field. Okay, they come in a certain number. Okay, so m running from 1 to the number of p forms, which I call np. Okay. Then we have the fermionic sector. Which contains the gravitinos and other fermions. Okay. In this first part, I will focus only on the bosonic sector, not because the fermionic sector is unimportant. That's not true, because all the structures I will describe, the global symmetry structure I will describe, follows from supersymmetry. And therefore, the bosonic sector and the fermionic sector are equally important in this game. Okay? It's just because in the fermionic sector, the action of the global symmetry is manifest. Okay, is more evident. Then I will also show how the global symmetry acts on the fermions.
For the forms, you're counting indices up to D or up to NP?
Oh, okay. Yeah.
So that means, are you counting
mu is
dual forms
0
separately or
t minus 1. Okay.
so you're counting dual forms, conjugal forms separately?
Yeah.
For
For the time being, I'm just considering these forms. Okay, just now I will discuss the issue of duality. Okay, but for the time being, let us just write these fields like this. With P can be well, we can have different P forms. That is antisymmetric tensors of different ranks in the supergravity. Okay, as we shall see, we can there are equivalent versions of a single engaged supergravity in d-dimensions. Okay, and these are related by Hodge duality. Okay, dualization of these forms. Okay, now I'm coming to that.
And just a reminder, when you have a zero form, that's distinct.
That's a scalar.
Yeah, is it really a scalar? Is the scalar, like, should I think of them separate or?
No, they are inside.
Like
they are counted as scalars.
Okay, so mu does not need to be zero. Oh, sorry.
No. Mu is a space-time index.
Yeah. Yeah, so my question is how many components are you allowing there? If they go up to...
How many p?
Yeah.
Oh, okay, sorry.
You allow
Greater,
zero components or-
greater or equal than 1, sorry.
Yeah. And less than equal to d, that is.
There is a normal natural bound, upper bound. You cannot have an antisymmetric tensor of rank greater than d. That's the most you can have. So yeah, p is greater or equal than 1. Zero forms are counted as scalars, particular scalars which are called axons. Okay, but they are counted as scalars, so they are described within the scalar set. Okay. These P forms, well, these P, rank P tensors, they are also described as forms, exterior forms like this, by contracting it with a basis of this kind. Okay? So they can be described also as P forms. And in this case, well, this is a way of describing them which is manifesting invariant under diffeomorphism. Okay? So it is convenient in some sense. Now, what happens is that in extended supergravities, typically supersymmetry couples some of the scalar fields. Couples means transforms, connects some of the scalar fields to the P forms, to the P form fields. This means that if supersymmetry is large enough, and this is the case for extended supergravities, scalar fields and P form lie in the same supermultiplet. They are connected to one another by supersymmetry. For instance, in 4 dimensions, there are scalars which live in the vector multiplets, okay, which are connected to vector fields by supersymmetry, acting twice on them by supersymmetry. Okay. In in n equal 1, so in a minimal supergravity in 4 dimensions that is not extended, number of supercharges is 4 in that case. This is not the case in 4 dimensions because we have chiral scalar fields living chiral multiplets, and they are connected only to sigma half fields, but not to P forms. Okay, in this case, what happens is that supersymmetry fixes the couplings of the scalar fields to these P forms. Fixes the couplings of the scalar fields to these P forms through the kinetic term of these P forms here. Okay, I will show you now how this is done. So these couplings are fixed up to a residual freedom. Let us now write down for a P form like this the kinetic term. Okay. Let us now write down the kinetic term for a P form, the generic form. In the case in which D is different from 2D plus 1. So we first focus on this case because it's the simplest. Okay? Then we will consider also the case in which D is equal to 2 times P plus 1. And their situation, the form of the kinetic terms is more complicated. Okay, so what is the form of the kinetic term for these forms here? We can write it like this. This is square root of the determinant of the matrix, absolute value of the determinant of the matrix, divided by 2k factorial, where k for me is P plus 1. Okay? Times an epsilon, which is minus k minus 1, which is minus 1 to the p, times a matrix, depending on the scalar fields, times f m mu1 mu k, f n mu1 mu k. Okay? This is the form, the expression of the kinetic term of a B form, such that this is true. Okay? Has this simple expression here. Notice that in the kinetic terms, the kinetic term depends on the scalar fields. The scalar fields enter the kinetic term. This is a general feature of supergravities. This is a general feature. And the scalar fields which enter here are those which are connected to the B forms by supersymmetry. And supersymmetry fixes this coupling, namely, supersymmetry fixes this matrix here. Up to some residual freedom in the choice of bases, okay? A redefinition of the field strengths, linear redefinition of the field strength. But up to this, supersymmetry fixes this matrix, which defines the coupling of the scalar fields to the B form, okay? This is an important feature. Now, let's write down the definition of this Fm. Fm is equal to d, which is a K form, is dCe. Okay? So, M. So, the Bianchi identity is simply dFm equals 0. Okay, that's very simple. Because d squared is equal to 0. Okay, now let us write the equation of motion for these fields. To write the equation of motion is useful to define a dual field strength. Let's define it here. Gm mu1 mu d minus k is equal to epsilon times epsilon mu1 mu d minus k mu1 mu k delta L over delta f and mu1 mu k. Basically is this epsilon tensor, which I always define as epsilon 0, 1, d minus 1 equal 1. Okay, that's the usual definition. Times the variation of L with respect to f.
So is your epsilon tensor density, or is it?
This is just that. Yeah.
So if you put the square root of g in front, or
it's inside here.
oh,
The square root of g is inside here. So it comes from L. Okay.
sorry, maybe this one that that's because I get confused. Are we always in Einstein frame, or
We are always in Einstein.
okay, so no straight frame, but
No. So when we perform the compactification, dimensional reduction, we rescale the matrix, or we write the general form of the higher dimensional matrix, so that the lower dimensional one is in the Einstein frame.
okay. So the dilaton is just one of the scalars, and
The dilaton is just one of the scalars.
It doesn't have a special role.
That's right. No, it doesn't. It's one of the scalars. But you can identify it clearly. Very
It has specific couplings.
Sure. Choosing the parameterization of the scalar manifold aspects, you should see. In a switchable way, you can identify, you can pinpoint all the high dimensional, you can manifest the high dimensional origin of all the scalars. Okay, so this is the definition of this GM, and you can verify that GM, do the variation of this guy, GM is nothing but, as a D minus K form, this is a D minus K form, is nothing but minus mn phi star of Fn. Okay. Now I'm going to define the star operator. Okay. The star operator is the so-called Hodge operator. It is defined in this way: star of omega mu 1 mu p, or call it mu 1 mu l, okay, l. This is equal to square root of g epsilon mu 1 mu l mu 1 mu d minus l omega mu 1 mu d minus l divided by d minus l factorial. This is the definition of the Hodge dual operator. Okay. This is the definition of the Hodge dual operator. So you see, it maps an L form into a D minus L form, or better, a D minus L form into an L form. So it will map a K form into a D minus K form. Okay? Now, how do you write the field equations? The field equation for the P form field. Well, you can easily verify because G already contains the variation of L with respect to F. Sorry.
So we started off with a bosonic sector which had P forms, right?
Yes.
And now some of them are Hodge dual to one another, right? Are we not double counting, or have
No. So far, no. So far we have a formulation of our engaged supergravity containing a number of P forms. Now I will show you that how, P forms are dualized, so how you can construct out of a formulation an equivalent one by using this Hodge duality. Now I'm just focusing on one P form and its description. Description in terms of Bianchi identities and field equations. You easily verify that the field equations, so while the Bianchi identities are df k m equals 0, the field equations are d g d minus k m equals 0. Notice that here this index is up and here the index labeling, the corresponding forms, is down. Okay, this will be related to a specific transformation property with respect to the global symmetry group. Okay, so the position has meaning, contravariant versus covariant, with respect to a suitable group, which we are going now to define. So these are the Bianchi identities and the field equations. You can verify that the field equations have this form. Okay, now we can dualize the P forms, Cp, into dual C tilde D minus P minus 2 forms. How? Simply by writing Gm D minus K, which is D minus P minus 1, remember how K is defined, okay, as D of Cm. D minus P minus 2. Okay, tilde. By writing these, okay, as D of this other object. Okay. So while in our original theory, the fields which are locally described in the Lagrangian, that is the elementary fields, are CD, we can define an equivalent version of the theory in which the elementary fields are C tilde. How do we do that? Well, it's a kind of Legendre transformation. It's a kind of Legendre transformation in which you add to the Lagrangian a coupling like this. L, you add to it a coupling like this. F, M, wedge, G, M minus D, C tilde M. Okay? You add a coupling like this. Okay? Then you extremize with respect to F. Equals 0. And this implies another, well, this gives you another Lagrangian which contains now only G. This is the way in which you dualize. And you see, this is a kind of Legendre transform that you do. The new Lagrangian will describe the C tilde together with all the other fields instead of C. The elementary fields of this new Lagrangian are C tilde. This is equivalent because these two are equivalent ways of describing the same degrees of freedom. So they are just equivalent formulations. But you're trading Fm for Gm. Now, what you're doing is, you see in the new formulation, in the new Lagrangian, in the new theory, which is the dual theory, now D, Gm equals 0 are the Bianchi identities. The same now are the Bianchi identities because G, M are D of C tilde. And D, F, M equals 0 are now the field equations. So what you're doing by dualizing, okay, you're exchanging both Bianchi identities and field equations. Now, it turns out that I will show you why equivalent formulations of an engaged supergravity, of a same engaged supergravity obtained in this way, differ in general in their global symmetry group. The global symmetry group will be different, or may be different in general. Okay? So if I do this, what changes is the global symmetry group of the theory, meaning of the field equations and Bianchi identities. The reason for this is that, as we shall see, the global symmetry group of an engaged supergravity is related to the geometry of the scalar sector. More specifically, it is determined by the isometry group of the scalar manifold. The scalar fields are described, as we shall see now in a moment, by a nonlinear sigma model. The global symmetry group is the isometry group of this nonlinear sigma model. So, the symmetry group of this nonlinear sigma model. If we dualize forms, okay, in this way, in general, this will change the number of scalar fields and change the geometry of the scalar sectors. For instance, if we are in 4 dimensions and we have 2 forms in 4 dimensions, okay, we can choose to dualize the 2 forms into scalar fields. In this way, we are increasing the number of scalar fields, and also the structure of the scalar manifold will be different. And also the global symmetry, the isometry of the scalar manifold. Okay,
So,
yes.
just to clarify, global symmetry means the isometry group.
Yes, I will. Now I'm going to show why.
Well, because in Andre's case, there are 2 kinds of group. One is E7, exceptional, and another one is for the abelian vectors. Is it?
But that, okay.
So when we
E77, I'm talking about the global symmetry loop. So the global symmetry loop is E77 in the maximal supergravity.
yeah.
In the case of, but in a specific version of maximal supergravity. For instance, if you compactify 11-dimensional supergravity on a torus, okay, you end up with, on a torus down to 4 dimensions, okay, you end up with forms of various ranks, okay. The scalar sector there does not have an E77 symmetry. But what you can do is you dualize the two forms, of all forms to lower rank forms. Okay? In doing this, of course, you will in general be increasing the number of scalarities. In the version in which you dualize all forms to lower rank forms, okay, and therefore the scalar sector is maximal, okay, you have the maximal amount of global symmetry. You have the maximal isometry, because the scalar manifold is maximal in that case. And in that case, you have E77 in 4 dimensions, E66 in 5 dimensions, and so on. So only when you dualize all forms to lower rank forms, then you have these exceptional groups in the maximal theory. Okay? What you mean by symmetry associated with the vector fields, no? Well, these are the local symmetries. The local symmetries, the gauge symmetries, which are trivial in the ungauged case, because nothing is charged. In the ungauged case, it's always U1 to the number of vector fields, and nothing is charged with respect to them. They're always there. Okay, good. So let us see how global symmetry acts on these. By the way, this relationship between duality symmetry G, right, G, and these duality covariant, these duality related formulations of ungauged supergravity was discussed in paper originated in a paper by Kremer, Juliat, Yu and Hope, called the dualization of dualities. So this dependence of G, of the global symmetry group, on whether we describe the same degrees of freedom in terms of C or C theta, that is called the dualization of dualities. Okay? So, how do global symmetries act on okay, let's use this on P forms. Let's use this expression of the kinetic term for the P form. You see that if we transform Fm with a linearly by a constant matrix, which I call S, let's call it S minus 1, n, Fn, I transform it like this. And if I transform Mn as this way, you see, if I transform F, the field strength, in this way, and the matrix M in this way, you see that the kinetic term is left unchanged, because all these S matrices, they just cancel out. Indices are constructed in an invariant way, so that they will cancel out. Okay. So global symmetries on P forms, they just act linearly as a transformation of this kind. However, here there is a subtlety. What subtlety? Well, M is not an independent field and depends on the scalar fields. Okay? So, in order for this to be a symmetry, it has to follow from a corresponding variation of the scalar fields. So this has to be equal to M of a suitable phi prime. Clear, because symmetry means that the equation motion and derivatives have to be invariant in form. Okay? And therefore M must have the same form, but as a function of transformed scalar fields. Okay? Okay. So, a global symmetry transformation of, so a linear transformation on the B form, it must be combined with a transformation on the scalar fields. Necessary. This is related to the fact that these B forms couple to the scalar fields because of supersymmetry. So there's supersymmetry behind every step of these derivations. Okay? Okay, so let's describe scalar fields. How are scalar fields described? Well, let us write the most general kinetic term for the scalar fields that we can write. Let us write the kinetic term. We have d nu phi s d nu phi r, where s and r run from 1 to n s, number of scalar fields. Okay? Then we have 1/2 here. Remember, we are in mostly minus sign. And here we have two free indices. Okay? So I can still construct this by a matrix GRS, which is itself functional scalar fields. Now, scalar fields, they can occur nonlinearly in the action because they don't carry space-time indices. Okay, so this matrix can be a linear, nonlinear, and in general is a nonlinear function of the scalar fields. This is the most general thing we can think of. Of course, there has to be a square root of G. Okay? This is the more general expression we can work out for the kinetic term of the scalar. But the positivity condition on the kinetic term, the condition that there should be no ghosts, implies that G Rs, namely this function here, has to be positive. Now, this is the Lagrangian of a nonlinear sigma model. Nonlinear sigma model, in which, you see, we can consider the scalar fields as coordinates on a manifold, the scalar manifold. Remaining one is the external manifold, d-dimensional spacetime, and the other one is an internal manifold, the scalar manifold, of which scalar fields are coordinates. Okay? Now, we have seen that in order for this transformation, for a linear transformation on the C form to be, or the B form to be a symmetry, it has to be combined with a corresponding transformation on the scalar field. much time do we have?
I mean, whenever it's a good time to take a break, we can. We're about on our.
Okay. I'll just finish one here, one of the videos. So this transformation S should correspond to a transformation on the scalar fields. Okay? Now, in order for this to be a global symmetry of the theory, this transformation on the scalar fields must leave the scalar action in bath. Now, the scalar action is not in bath. The line element on the scalar manifold. So, symmetries of the scalar action are the action is clearly invalid. You can easily verify this. The action is clearly invalid. Okay? Because the derivatives will change precisely by this Jacobian. Okay? And you easily see that the action is invalid. Okay? So S should correspond to isometries. This is a necessary condition for a linear transformation on the p-forms to be a global symmetry of the theory. It implies a transformation on the scalar fields. The transformation on the scalar fields is a symmetry provided it is an isometry. Is this true also? Is it also true the reverse? I mean, does any isometry correspond to a linear transformation of this kind on the fields? I will answer after the break. Okay?